Section 2-1, Reasoning and Logic. And we're just going to scratch the surface of these topics, so we're calling this an introduction. In this section, we'll talk about quantifiers and statements. We'll talk about logical equivalence. We'll also talk about developing logical arguments and the validity of an argument. First, let's start by defining what a statement is. A statement is a sentence that is either true or false. See a typo here, call that or. False, not of, false. So I have a few things written on the screen and we want to go through and decide which of these are statements. We'll know it's a statement because we can agree that it's either true or it's false. So let's start with the first one. So if we say she, we're not being very specific about who we're talking about. Maybe we're talking about Taylor Swift. In this case, the statement would be true. She does have blue eyes. Or maybe instead we're talking about Britney Spears. It would be false. She doesn't have blue eyes. So this statement depends on who she is. We're not being specific about who she is, and because each one of us could imagine a different she, this statement changes from true to false depending on who the she is, which means we can't agree whether or not this statement, as it's written, is true or false. It's not a statement. Because it can be both true and false depending on who she is, this is not a statement. What about the next one? So we have x plus 7 equals 18. Well, what is x? Is x equal to 0? If it's equal to 0, then this is false. However, if it's equal to 11, then this is true. So this is not a statement because it could be both true or false. So we'll cross it out. What about the next one? 2 times 5 plus 7 is greater than 1. Well, 2 times 5 is 10. 10 plus 7 is 17. So what we have on the left-hand side is 17. That's greater than 1, so this is true. Because we can agree that that's a true statement, because we can agree that this is true, we know it's a statement. I'm going to use these 3 little dots that look like a triangle. Those dots actually mean the word therefore. It's a shortcut to write the word therefore. I can draw 3 dots instead of writing out the 8 letters that are in therefore. So I'll say true, therefore, statement. What about the next one? 2 plus 3. Well, this isn't true or false because 2 plus 3 is actually a direction. It's not a statement. How about the next one? The question, how are you? Well, that's not a statement. It's not true or false. It is a question. So we had a direction and we have a question. These are not statements. The next one, the jogger ran from the neighbor's dog. Now this is kind of tricky because the jogger is talking about one specific jogger. If this were a jogger instead of the, it would change completely. But the jogger is referring to the only jogger that you could be referring to, and this jogger ran from the neighbor's dog. So this is either true or false, but it is a statement because we're talking about one jogger. So if we're talking about somebody running down the street, we can say that is the jogger. We don't know if it's true because we don't see the jogger or the dog. We don't know it's false for that same reason. But we know that it is either true or false because it's talking about very specific things. It's talking about the jogger and it's talking about the neighbor's dog. Let's look at the next statement. Lincoln was the best president. Now this one's tricky too. Lincoln, that's specific. President, that's specific. But the word best. This is an opinion. So depending on who holds that opinion, this could be true or false. This is not a statement, it's an opinion. So things like directions, questions, opinions, those are not statements. They're different kind of sentences. Let's look at a few more. Jenny has blue eyes. Well, Jenny is a specific person, and either she does or does not have blue eyes. My mom's name is Jenny. She does not have blue eyes. So I would say it's false, but it's still a statement. And that can get a little hairy. Maybe you're thinking, well, there's multiple Jennys out there. Which Jenny are we talking about? We don't want to split hairs about it. This is a statement because it's referring to a specific person and it's that person's specific qualities. All right, let's move on to the next one. 5 plus 7 equals 18. That is an equation that is false. Because it's false, we know that it's a statement. Statements are things that are either true or false. If we had written a true statement, then we would say true, therefore statement. But in this case, we have something that's false written down, and so we say it's false, and because we know that it has a truth value of false, it's a statement. Next one, 2 times y plus 7 is greater than 1. Well, what if y is negative 100? It would be false. What if y is equal to 0? It would be true. This is not specific enough, not a statement. What about 2 plus 3 equals 5? That's true. It has a truth value, therefore it's a statement. Next one, I am happy. That's a little tricky because either you are happy or you are not. I is a specific person. Happy is the quality that that specific person has. This would be a statement. Whether it's true or false depends on if you are or are not happy. Next one, look out. That's not true or false, that's a direction. Not a statement. Next one, Lincoln was the first president of the United States. Either this is true or it's false. Hopefully we know the truth value of this statement. Lincoln was not the first president of the United States, so this is a false statement, but because it has a truth value, even though it's false, because it has a truth value, it's a statement. So deciding if something is a statement or not, what you need to do is ask yourself, is this something that is true all the time? Or is this something that's false all the time? And if the answer to those questions is a yes for one of the two questions, then it's a statement. If, however, you say, well, I don't know because I don't know who she is, or I can't decide if this is true or false because it's a direction that's being given to me, or this is a question that you're asking me. Questions can't be true or false. Or is it an opinion? Hey, that's an opinion. I don't want to be the judge of whether or not that is a pretty color or it is not a pretty color. Those are opinions. So statements have to be true all the time, or they have to be false all the time. They can't be in limbo. Now that we know what statements are, they're sentences that have a truth value, and that truth value could be true or it could be false, but it has to be only one of those. We can talk about how to change those statements with negations and quantifiers. A negation takes whatever value a statement has and it reverses it. So if I make a statement like, my name is Joe Fauna, then the truth value is that's true. The negation of that would make that statement false. So I would say something like, my name is not Joe Fauna. So negations reverse the truth value of a statement. Quantifiers tell you the quantity that a statement applies to. We have two specific types of quantifiers. Universal quantifiers, which tell you that the statement applies to each and every element. These are words like all, every, or none, or no. Or we have existential quantifiers. These quantifiers refer to one, maybe two, maybe three, maybe all of the elements, but not necessarily all of them, just a possibility of all of them. And these are words like some or there exists. Now that we know what the quantifiers are, we can take a look at some examples. So we have a few statements here. Each statement involves a quantifier. And then on the next side, this second column, I have the negation of that statement. So if I say something like, some A's are B's, whatever A's and B's are, and I want to negate that, I need to take the quantifier some and turn it into none or no. And I can use this little diagram at the bottom of the screen to help me with that. So if I'm saying something like some are, I would follow the arrow to the opposite. So negation means go to the opposite, and that would tell us to do none are. Let's look at the next one. Some A's are not B's. We need to use our quantifier table to change from some to all. So some are not. We have some and are not. We'd follow across that arrow to say all are. Moving on to our next statement, all A's are B's. If we're saying all are, then the negation of that follows that arrow down to some are not. So we would say some A's are not B's. We have one left. No A is a B. So we look at our table. We don't have anything that just says no, but none is pretty much the same thing as no A. So none of the A's are B's. So no A is a B. We follow that down the diagonal for the negation, and it says some A's are B's. Now, quantifiers and the negations can be a bit tricky. In fact, if you've ever taken a logic class, this is something that many students struggle with. So try not to get too overwhelmed with statements, quantifiers, and negations of those quantifiers. We have this little table that will help us sort it out, and that should be decent to help us get through the section. We're not going to test heavy on this, but I want the idea to be clear that you can have a quantifier in a statement, and the negation of that quantifier changes you from a some to none, some are not to all changes to some are not, and none changes to some are. So if we can follow this table, then I think we will be fine. Truth tables are something that we can use to help determine the truth value of a statement. And it can also help us to see all the possibilities for the value of a statement. So there's this puzzle called Lady or the Tiger, and it's a puzzle about a prisoner who has to make a choice between two rooms. Each room has a sign on the door, and only one of the signs is true. So we have two doors. Basically, he's going to open one of these doors. And before he opens the door, he's going to read what's on the door. The two doors have the following signs. One door says, in this room, there's a lady, and in the other room, there is a tiger. The other door says, in one of these rooms, there is a lady, and in one of these rooms, there is a tiger. Now, reading these, they both seem like they could be true, but we know that exactly one of these signs is true, which means one of these signs has to be false. So we have to go through and figure out which one is the true sign and which one is the false sign. He doesn't want to open the door and find the tiger. Probably the tiger would kill him. He'd probably rather open the door and find the lady, because chances are the lady won't kill him. But then again, who knows? I mean, I've watched some crazy documentaries. Anybody could be a killer, right? Just kidding. The lady's going to be a nice lady. She's got like a sandwich waiting for him. So he wants to open the right door, but he needs to think about which door is the right door to open. So let's go through the scenarios. Only one of these signs can be true. So maybe we pick one of the signs and we say this is the true sign. If this sign is true, then there's a lady inside of this room and there's a tiger inside of this room. Can I draw a tiger? This is what you get for a tiger. Stripes. Meow. Whatever. So if that left door is true, then we know there's a lady in this room, there's a tiger in the other, which means the second door has to be false. Reading that sign, in one of these rooms there is a lady, and in one of these rooms there is a tiger. Well, that doesn't sound very false at all. That sounds less like a false statement and more like a true statement, because in one of these rooms there's a lady, and in one of these rooms there's a tiger. That would mean both of these are true, which we know can't be true. This is the case, only exactly one of these can be true. So we've run into a contradiction. Instead of considering the case where this first one is true, let's consider the case where it's the second sign that's true. That one starts off by saying, in one of these rooms there's a lady, and in one of these rooms there's a tiger, which means the lady could be in this first room, or she could be in this second room. If the lady's in the first room, then the tiger is in the second room. If the lady's in the second room, then that means the tiger has to be in the first room. I'm trying to draw legs on this tiger. Get out of here. Okay, that tiger doesn't get front legs. Sorry. So if the second door is true, then we either have this case, case 1, or this case, case 2. In case 1, the lady is in the first room, the tiger is in the second room. In case 2, the tiger is in the first room, the lady is in the second room. So if we're starting with the assumption that the second door is true, the only way for us to figure out the real case is we need the second door to be false. So if the first door is true and the second door is false, then scenario 1 won't work, because scenario 1 agrees with what's written on the first door. So it would have to be scenario 2, because if scenario 2 is the right one, then it says that there's a tiger in this first room, not a lady. But what's written on the door there says there is a lady in this room. So if I put the tiger in room 1 and the lady in room 2, then the second door is accurate. There is a lady in one room and a tiger in the other. But the first door is false, because the first door says in this room there's a lady, but actually we know it's a tiger. Now that might have made your head spin just a little bit, and that was the point, unfortunately. I wanted to show you that trying to consider all the possibilities for a true or false outcome, it can be really complicated if you're just thinking about it in your brain or even drawing very terrible pictures. But a truth table will help you sort through all of that without letting your head get spinny. And that's because truth tables are used to show all possible true-false patterns for a statement. So for example, if we say that a statement is false, the negation of that statement, I said that backwards. If we say that a statement is true, then the negation of that statement becomes false. If we say that a statement is false, the negation of that statement becomes true. So what we did here is we said only one of these can be true. If the first one is true, then we have a lady in one room, a tiger in the other. We need the second one to be false. So we had to negate that second statement. And the negation of that second statement is what gave us the tiger in the first room, the lady in the second room. We're going to use truth tables to determine the truth value of different types of statements and the combinations of statements. So we'll see that more in just a second. Compound statements are when you take two statements or more and you combine them. So we're going to look at two different compound statements, a conjunction and a disjunction. Now, statements are usually sentences, and we're going to try and abbreviate our work here. Statements are sentences, but we're going to represent them with a letter, like P. So if I say P, what I mean is a sentence that has a true or a false truth value. So when I talk about a conjunction, and I call it a compound statement, I'm talking about two statements, P and Q are the statements. Those are both sentences that are either true or false. So the conjunction, P and Q, that's how we read that, is defined to be true if and only if both statements are true. So we're going to make a truth table to help us sort through this, and we're going to use some examples to make more sense of it. The first statement, P, Joe eats fries. The second statement, Q, Maria drinks soda. These are either true or false. Either Joe is eating fries or he is not, and either Maria drinks soda or she does not. P and Q says Joe eats fries, that's the P, and that's the little upside down caret thing. Maria drinks soda, that's the Q. So this is a symbolic way of representing the statement Joe eats fries and Maria drinks soda. So we're going to use those two statements and the conjunction to fill out a truth table just for good practice. When we make a truth table, you need to have one column for each statement. And then you probably should have a column for the thing that you're trying to find the value of. So we have a conjunction column. We're going to start with a blank table and we're going to fill it in together. The statement P is either true or false. The same for the statement Q. Now I'm going to fill this out in a kind of chaotic way first, and then I'll show you how to make it simpler. If statement P is true or false, I could start by filling out one T and one false. But then if statement Q could be either true or false, I can see that I'm really only considering 2 of 4 statements. I'm looking at either both of the statements being true, or I'm looking at both of the statements being false. But I'm sure we could imagine a case where the statement P is true and Q is false, or where the statement P is false and Q is true. Now, filling this out required us to think quite a bit about all the possible combinations, which is why I don't really like filling it out this way. We do have all 4 combinations, so that's great, but to make sure that we have the best of all 4 combinations, I like to fill it out this way. I like to keep all the possibilities where P is true together. So P could be true and Q could be true, or P could be true and Q could be false. Now that I've gone through all the possible scenarios where P is true, I'm going to go through all the scenarios where P is false. P could be false and Q could be true, or P could be false and Q could be false. And this is more of a systematic list where I go through all of the possibilities where P is true, and I'm going through Q true first, then false. Then I go through all of the possibilities where P is false, then I go through Q true, Q false. So same order in the Q column. And this is a little more organized, I think. Anyways, now that we have our 4 different scenarios drawn out, we need to determine when the conjunction is true and when it is false. So the definition says that P and Q is defined to be true if and only if P and Q are both true. So in our first column, I have P true, Q true, the conjunction is also true because both statements were true by themselves. Looking at the next scenario, we have P is true, Q is false. That does not meet the criteria for the conjunction to be true. Only one of those statements was true, the other was false. Therefore, the conjunction is also false. In the next scenario, P is false, Q is true. Again, that fails the conjunction because the conjunction needs both things to be true. And then lastly, we have two false statements, and this is almost like two wrongs don't make a right. This conjunction would be false here as well. So a conjunction is defined to be true if and only if we are in this first scenario where both statements are true. So when you read this symbol, P caret Q, we'll read that as P and Q, and in our mind we'll say, in order for P and Q to be true, each has to be true by themselves. So P has to be true and Q has to be true. Now let's look at a disjunction. Again, we're going to look at two statements, statement P, statement Q. Statement P says the clock is slow. Statement Q says the time is correct. A disjunction with the symbols P upside down caret Q, we read that as P or Q. This type of junction, this compound statement, disjunction, is defined to be true if and only if either P or Q is true, and we're going to take a second to talk about what inclusive or means. Either or usually is like, pick one. Either you want to have coffee for breakfast or you want to have orange juice for breakfast. Usually we don't get both. It's one or the other with our little combo meals. But inclusive or says, hey, if you want coffee and orange juice, go for it. So there's three ways to make this compound statement true. If P is true, the compound statement is true, no matter what Q is. Or if Q is true, the compound statement is correct, it's true, no matter what P is. Or they could both be true. So there's three ways to make this work. And we'll show that in our truth table. So we can plug our sentences into the symbols to say the clock is slow or the time is correct. So we have P or Q. And we're going to fill that out in our truth table. Our truth table looks very similar to the one for conjunction. The only difference is that the last column is a disjunction. We'll fill out all the possibilities for the truth values of P and Q. So P could be true, Q could be true or false, or P could be false, Q could again be true or false. So we have all four different combinations here. Remember, for a disjunction, we only need to see one T. So in our first row, we have one T. We happen to have two T's, so it's true. In the second row, I have one T, one F. All I need is one, so the disjunction, true. Third row, one F, one T, perfect. We have the T we need. We can ignore the F. All we need is one T. And in the last row, I have one F and two Fs. There's no T's down here, so this junction would be false if both P and Q are false. Truth tables can also be used to determine if two statements are logically equivalent. Now, if we're just looking at P and Q, this can be very simple. For example, if I list out all of my possibilities for P and Q, I have true, false, true, true. That's not the order I like to do it. Or I could have false, false, true, false. In this very general case, P is not logically equivalent to Q because we can see that sometimes these statements have different truth values. It's possible that they could have the same truth value, but it's not guaranteed. So if we want to check if two statements are logically equivalent, what we need to do is fill out a truth table to talk about all the different scenarios and make sure that the statements match. We're going to fill out this huge truth table to show that this is a logically equivalent statement. So we have one statement on the left which talks about P and Q negated. And then we have another statement on the right which says negated P or negated Q. To build this, we're going to start with the simple 2 columns, one for each of the 2 statements we're looking at. We need to fill out all the possibilities for P, all the possibilities for Q. So P could be true, Q could be true. P could be true, Q could be false. P could be false, Q could be true, P could be false, Q could be false as well. I've got a lot of columns here because I like to do this piece by piece. So we have all of the possibilities for statement P, all of the possibilities for statement Q, and every combination of the 2. And now I'm going to build the left-hand side of my statement piece by piece. So we're going to start by doing the conjunction, P and Q. We just did this table, so we could just copy it down, or we could think about it again. P and Q, the only time that was true was when both P and Q were true. Otherwise, that conjunction was false. But then our statement has the negation of that. So I'm going to do another column where I negate P and Q. Now, since I have P and Q in this column, I'm just going to negate each one of these truth values. So if it was true here in the negation column, it's false. If it was false here in the negation column, it's true. So then the next 2 entries will be true as well. So because I did this piece by piece, I don't have to go back and recalculate P and Q. We already have that. The negation column is just looking one step back. So this is the left-hand side of our statement. Now I need to build the right-hand side. So we have the left-hand side finished. We need to build the right-hand side now. The right-hand side has the negation of P. It also has the negation of Q, and then it has the negation of P or the negation of Q. So I'm going to do each of these statement negations first. To fill out this column, I need to look back to the P column so that I can negate each of these truth values piece by piece. So in the first column, P was true. So in this 5th column, not P would be false, false, then true, true. So I've just switched all of the truth values compared to the first column. Then I'm going to do that same thing for Q. So to fill out not Q, I need to look back at the Q column. I'm just going to reverse each of these truth values. So we had true for the first entry, not Q would be false. We had false for the second entry, so not Q would be true. And then we would follow false and true again. So we're just swapping the truth value for whatever we had in column 2 over here in column 6. Now that we have not P, we also have not Q, we can do the OR. Remember that the OR is true as long as one of these is true. So we're going to look back to the previous 2 columns, and we're going to decide if the disjunction is true. In the first scenario, we have false with false. That disjunction would be false. In the second scenario, we have false with a true. We have the one true we need. Third column, we have a true, so that would be true. And then the fourth column, we have 2 trues, so that's true. So what we did was calculated the right-hand side. And we did that by looking back to the previous 2 columns. We didn't have to go through and recalculate everything. So I really like breaking this down that way. Now, to determine if it's logically equivalent, we need to show that in the exact same conditions, the left-hand side and the right-hand side have the same truth value, which means for the first scenario, the left-hand side was false, the right-hand side also has to be false. Second scenario, they match, they're both true. Third scenario, they match, they're both true. Fourth scenario, they match, they're both true, which means we've showed in every possible scenario the statement that says that these two statements are logically equivalent is true. We can use that equivalence symbol to say that they will have the same truth value at the end of the day. Conditionals and biconditionals are another type of compound statements where you take two statements and mush them together. The notation for a conditional looks like P pointing to Q, and the way that we read this is P implies Q. Or we write that as if the statement P happens, then Q will happen. So we're going to, again, use an example to go through this and fill out a truth table. So we have an implication. Betty promises that if she gets a raise, she will take you to dinner. So let's break this down into a PQ type situation. The if, well, what are they saying if? If what? If she gets a raise, that's P, that's our hypothesis. Then is what happens if that raise is given to Betty. We don't see the word then, but we can feel that the implication is that if she gets a raise, then she will take you out to dinner. So this is our Q, the conclusion. We have each of our statements, the hypothesis, P, Betty gets a raise. Q, Betty takes you to dinner. Let's go ahead and put that into a truth table so that we can get an idea of the different scenarios that are out there. Remember that we have all the different possibilities for P and Q, so we'll fill those into our table. And I want to take a second to decode what two truths is. So if both P and Q are true, that means Betty gets the raise and Betty takes you to dinner. So that totally satisfies the implication. Both statements being true means that the conditional, if P then Q, is also true. She kept her promise. We're happy. In the next one, if P is true, then Betty got the raise. But if Q is false, then she does not take you to dinner. We're probably not happy about that. She did not make good on her promise. The implication or the conditional is false. Next scenario. If P is false, then Betty does not get the raise. Sorry, Betty. So sad for you. And if Q is true, then she still takes us out to dinner. That makes us happy, but it wasn't necessary. She didn't say, I'm going to take you out to dinner no matter what. She said, I'll take you out to dinner if I get the raise. So in this case, the initial hypothesis was false, but we have no idea what that means for the implication. If you don't meet the hypothesis at the beginning and she takes you out to dinner still, did she actually break her promise? No, she didn't break her promise. So although the hypothesis is false, we're going to say that the implication is still true. Almost to say she kept her promise, or to be more accurate, she didn't break her promise. And then what about the last scenario? Again, P is false, so Betty did not get the raise. Betty also did not take us out to dinner. If we say Q is false, then she did not take us out to dinner. But did she break her promise here? No, she didn't break her promise here either because she never said what would happen if she doesn't get the raise. Which means that the implication is still true. And this is something that many students struggle with. The implication is almost always true, except for one case. The only time an implication is false is if the hypothesis is true, but the conclusion is false. So this is the only way for Betty to actually break her promise, is if she gets the raise, but she does not take you to dinner. The last topic that we need to talk about in this section is valid reasoning. Now, valid just means that the argument follows unavoidably from the hypothesis, basically saying it could not be interpreted in any other way. So here's a hypothesis. All dogs are animals. Goofy, the Disney character, is a dog. Those are two separate statements. We're assuming that both of those are true. Those are our hypothesis. And we can draw this using a diagram of circles. If I draw a circle that represents all of the animals in the world, I know that I can draw another circle inside of it that represents all dogs. Now it's important that I have that circle inside of the animal circle and I don't have all dogs outside of it. If I had the circle outside, then it would say that dogs are completely separate from animals, but they're not. They are part of the animal family. I also don't have all dogs partially overlapping, meaning some dogs are animals, but some dogs are not. That's weird. I don't think, well, let's not get into dogs that aren't animals. So we have all dogs inside of the animal circle, which means anything inside of this all dogs circle also has to be inside of the animal circle. Goofy, we are told, is a dog. So Goofy has to live within the dog circle, but the dog circle is within the animal circle. So we get to make the conclusion that Goofy is an animal. That's probably the simplest logical argument, where everything narrows down into smaller and smaller circles, and every small circle fits into one of the bigger circles. Let's take a look at another one. All elementary school teachers are mathematically literate, meaning they can do math. Maybe they don't like it, but they can do it. They know what they're doing. That's one of the hypotheses. The second one says, some mathematically literate people are not children. Okay, let's break this down into some circles. We'll start with a circle that represents anybody that's mathematically literate. This could be the school teachers. This could be the kids learning from the school teachers. This could be anybody who's mathematically literate. It could be me, it could be you, it could be your neighbor, probably not your dog. And then we're going to draw a circle within the mathematically literate circle because the hypothesis says all elementary school teachers are mathematically literate, which means the circle has to be completely inside of the mathematically literate circle. I can't draw it half on, half off, because this would suggest that there are school teachers that are not mathematically literate. And even if that is the case, that's not what our hypothesis says. So remember, we're not here to judge whether or not these are true or false. We are trying to use those as true statements to draw a diagram. Next, we need to represent some mathematically literate people are not children. And that can be a little difficult because I could draw that completely outside of both circles, because some could refer to 1, 2, 3, or maybe all of them. So some is very vague. Or I could move that circle to where it's a little bit on top of the mathematically literate, a little bit not on top. So if we did it this way, then we're saying there's some children who are mathematically literate. They're inside of that circle. But then there's some children that are not mathematically literate. They're outside of that circle. And that still is valid based on the hypothesis that we're given. Or we could even draw this another way. In the last circle, we were not including elementary school teachers at all. But now in the new position that I've moved it, I'm saying that if I put a dot right here, that dot belongs to the children's circle. It belongs to the elementary teachers circle. And it belongs to the mathematically literate circle. If I put a dot between these two, right here, this would be a child that is not an elementary school teacher, but that is mathematically literate. Or I could have a dot out here where it's a child, not an elementary school teacher, not mathematically literate. So we've drawn our circle in a few different ways, and we want to consider all of them that could be possibly true. The way that this circle is drawn, we're assuming that it's possible for a child to be an elementary school teacher. But that might not be the case. You might think, there's no children out there that teach elementary school, and I'd agree with you, at least in my limited experience. So we've drawn all of our possible circles. Now we're going to check to see if the conclusion is valid. So we're not coming up with this conclusion. We're checking to see whether or not this conclusion is valid. The conclusion that we're checking says, no elementary school teacher is a child. So can we draw a circle of one of the three ways that makes that true? And making sure that we're still adhering to these two hypotheses. And this is where you're going to have to fight your instinct, because instinctually, you want to believe this conclusion. From our experience, this conclusion feels true. However, look at the diagram that we've drawn. This diagram does not violate either of the two hypotheses that we are given. However, the conclusion cannot be made with this diagram. It could when we had children circle over here, and it could when we had children circle over here. But remember, we have to make sure that the conclusion is true for any scenario that meets the hypothesis conditions. And we actually did find a scenario where that conclusion is not true, because the way that we have this circle, we could have some children who are elementary school teachers. So this conclusion, or this whole argument rather, is not valid. And the hard part about this is that you probably want to agree with this conclusion, but we're not here to say whether or not we agree. We're here to determine if the argument is valid, meaning can we represent the hypothesis in all possible ways and still arrive at this conclusion regardless of which way we orient our circles. Now, when we were looking at the dog and Goofy example, it was much easier because everything fit nice and neat. We couldn't draw the circles in any other scenario. It had to be this way. But with the school teachers and the literacy, we had various things that we had to consider, and one of them broke the argument. And that's all.